Hello everyone, this is Aidan for Fluid Mechanics 101, and today I'm going to be talking to you about what is the difference between yPlus and Y star. I'm very excited to bring this video to you today because there's a lot of confusion in the CFD community surrounding yPlus and Y star, and these are two metrics that are commonly used when assessing near wall and mesh resolution, and there's definitely some confusion surrounding the difference between the two metrics, how they're applied and how we use them. And in today's talk, briefly, I'm going to be going over what is the difference between yPlus and Y star, is it better to use yPlus or Y star, and what do modern CFD codes use? Do they use yPlus or do they use Y star? So to give you some background to start, to help narrow down and identify the problem here that we're actually talking about, got a diagram for you on the slide here which shows a free stream flow which is developing over some wall or boundary surface there, which you can see in blue. And as the flow proceeds along the boundary, a boundary layer or a region of slow moving flow develops close to the wall, as you can see there highlighted in red. And when we think about the problem overall, we may be in some global coordinate system with a Y, Z and X axis. But when we think about the boundary layer that develops on this surface itself, we see that the sharp gradients and the steep gradients actually occur very close to the wall. And if we want to analyze this near wall flow and reproduce it in our CFD model, we have to come up with some model for how that profile is going to develop as it moves along the boundary. Now, in order for us to do this, we need to have some measurement for our distance normal to the wall. As in a lot of these models, it's assumed that the boundary layer is very long, and so the only coordinate that matters is the distance normal to the surface, y. Now, for an arbitrary 3D geometry, this wall normal distance y is not necessarily going to correspond to the global coordinates y. It's going to be a local distance normal to the wall y. And we would like a measure of the distance of how far through that boundary layer profile we are. So how far away from the wall are we relative to the shape of the boundary layer profile? And if we know this, and we know how far we are normal to the wall relative to the shape of that boundary layer profile, then we can come up with a model for specifying how that boundary layer develops. Because ultimately in our CFD model, we need to ensure that the shape of our boundary layer is going to correspond well with experimental measurements for similar geometries. Now, we have to develop a special metric for measuring distance normal to the wall, and we're going to be using yPlus for that. And yPlus is a dimensionless distance normal to the wall. And the reason that we're using a dimensionless distance that's scaled on the flow conditions is for our geometry. If we were to change the free stream flow conditions or the shape and size of the geometry, we would want to ensure that our boundary layer profile still develops correctly and that it scales properly. And the way that we do this is by defining a dimensionless distance yPlus normal to the wall given there in equation 1. And we can see that the distance is going to scale on the dynamic viscosity, the density, and some velocity scale there. And that's as we expect, because very close to the wall, viscous effects are going to dominate, and so we expect the material properties of the fluid to influence this dimensionless distance. So now if we look at some experimental measurements and direct numerical simulations of the boundary layer profile, what we find is that the boundary layer profile actually has a relatively universal shape when we scale the shape of the boundary layer on this dimensionless distance yPlus. And as you can see from the plot there, yPlus, as we move along the x-axis increasing yPlus, the dimensionless velocity uplus also increases. And this velocity profile takes a very characteristic shape, as you can see there, and it turns out that this profile is relatively independent of Reynolds number close to the wall. If we increase the Reynolds number or increase the free stream flow conditions, the only real change to the profile is the shape of the profile at the far right end of the yPlus axis. So right out in the bulk of the flow, that's where we see the changes to the shape of the profile. But close to the wall, the velocity profile is relatively independent of Reynolds number, and this is excellent. So we can use this as a model in our CFD codes to ensure that our boundary layer shape is developing correctly. And the way that we do this is in our CFD code, if we can calculate a value of yPlus at some distance off the wall, then we know what the value of uPlus should be if our boundary layer profile is developing correctly. And for these experimental measurements, it's worth noting that they were carried out by getting a fully developed flow through two infinite parallel plates, as you can see there in the small diagram, developing a parabolic shaped profile, and then measuring the velocity at various distances off the wall, and then scaling the velocity and the wall distance based on the dimensionless quantities, which you can see there. So moving from the experiments to our CFD model, what we need to know is we want to know what the distance normal to the wall is for all of our boundary cells in our mesh. So we would like to calculate yPlus for all the cells in our mesh, and once we know yPlus, we can ensure that the velocity profile or the boundary layer that develops on that surface is correct. And the way that we do that is by correcting the near wall kinematic viscosity, which in turn ensures that the velocity normal to the wall is correct and corresponds with the experimental measurements that we saw there in the previous slide. And if you'd like to see how the near wall kinematic viscosity is corrected once yPlus is known, I did a previous video on this, which I'll link on this slide here and also in the description to this video, because that's not what we're going to focus on today. In this video, we're going to be focusing on calculating the distance normal to the wall yPlus and the scales that we use to compute that. So if we start with equation 2, this is the dimensionless metric for the distance normal to the wall, yPlus, and we've got density, a dynamic viscosity, a distance normal to the wall y in global units, and some velocity scale u. Now if we're quite close to the wall, viscous effects are going to be significant, and so we're going to take the dynamic viscosity of the fluid and the density of the fluid close to the wall for those metrics. Y is the distance normal to the wall, and at this point, what velocity should we take for our velocity scale? Now this isn't straightforward because the velocity at the wall is of course 0 by the no slip condition, and the free stream velocity, as we discussed earlier, has no relevance on the shape of that boundary layer that develops very close to the wall. If we increase the free stream velocity, that's going to affect the values of the velocity in the bulk flow or at very high values of yPlus, say 200 or 300. And so the free stream velocity actually has very little relevance on the universal shape of that profile close to the wall. So we also can't use the free stream velocity for our velocity scale. And at this point there are two choices that we could make for our velocity scale u, and we could either base our velocity on the square root of the wall shear stress, u tau, that gives us the correct units for velocity, or we could base our velocity scale on the square root of the turbulent kinetic energy, and you can see both of those expressions there in equation 3. We could use either. Both are mathematically sound and would give us a measure of the wall normal distance. And the terminology that CFD codes use to describe these two approaches is when we use a velocity scale based on the wall shear stress, we're using yPlus, whereas when we calculate a velocity scale based on the turbulent kinetic energy, we're actually computing y star. So the CFD codes use a plus and a star to denote that these two dimensionless wall distances are slightly different, even though they both play the same role in measuring a dimensionless distance normal to the wall for our cells. And as it turns out, the two metrics, when evaluated, turns out to be quite similar for the majority of flows. And you can always confirm this in your CFD code by post-processing yPlus and y star and confirm that they're in fact very similar. So we're going to start by looking at the yPlus treatment. Now, the yPlus treatment has been adopted historically for CFD codes, and the reason for this goes back to the original experimental measurements, where for the experiments we had essentially a flat plate boundary layer flow between two parallel plates, as we saw in the previous slides. And so in those experiments we would measure the velocity and the distance normal to the wall in global units, and then we could also measure the wall shear stress easily, and we could get the wall shear stress from the pressure drop by doing a momentum and force balance. So after having computed the wall shear stress in the experiments, we could take the square root and use that as a velocity scale to plot our velocity profile normal to the wall in dimensionless units. So that's the reason historically for using yPlus in the experiments, and yPlus was also used in early CFD code implementations as well. However, there's a problem with using yPlus for our dimensionless scale, and the problem is that we have to use iteration. And the reason for this is, if we look in equation 5, we have an expression for yPlus, which is given there on the left hand side, which is a function of wall shear stress, and then on the right hand side we've got an expression for the wall shear stress, which in turn depends on yPlus. So what that means is, for every cell in our mesh at the start of the iteration before solving the momentum equations, we would have to calculate yPlus and the wall shear stress iteratively for every cell in the mesh. And as we often have a large number of boundary cells, this quickly becomes very computationally expensive, as we have to do it during every iteration. And the way we might do that, we could propose an iteration scheme. And the way we would do that is take our two equations there, given in equation 6, we've got an equation for yPlus and an equation for the wall shear stress, and we can then combine these two equations together. And if you're wondering where that expression for the wall shear stress comes from, again, check out my previous video on wall functions and wall treatments for velocity, and that will explain how we get the expression for wall shear stress. And so to propose our iteration scheme, if we combine the two equations in equation 6 together, we reach equation 7, and the way I've chosen to do it is by squaring the yPlus equation on the left hand side and combining that with equation 6. And then what we can do is use some further manipulation, and that leads us to equation 8. And you should be able to follow through those manipulations fairly straightforward from equation 7. And what you'll notice here is that we have a single equation in terms of yPlus only, and it's written in the form of some function of yPlus equals to 0. So when the function is written in this form, equation 8, we can easily use a root finding algorithm such as the bisection method or the Newton-Raphson method to find the solution to equation 8 to give us our yPlus. And what we would have to do is we'd have to solve that equation 8 iteratively for every boundary cell in the mesh during every iteration. But we could do that to get yPlus. So how about y star? Now, in addition to wanting to avoid iteration, early CFD code adopters found that for flows where we have stagnation or separation points, the wall shear stress tau sub w becomes very small, and indeed with the case of separation, the wall shear stress will transition through 0 and become negative as the flow separates. And this can be quite difficult for the previous treatment of yPlus to deal with, because that expression, equation 8, can quickly become singular and lead to divergence. And what happened was Laund and Spalding proposed that instead of using yPlus as our metric for the dimensionless distance normal to the wall, we could use y star instead, where y star is dependent on the square root of the turbulent kinetic energy. And of course the reason for this was, even though those original experiments were done essentially on a flat plate boundary layer where we weren't going to be finding any separation or stagnation points. For more general flow conditions that we want to use our CFD codes for, these situations are quite probable. And so what we use in the Launder and Spalding approach is at the start of our iteration, in every cell in the mesh, we start by calculating y star from the turbulent kinetic energy that we computed from the previous equation, and then proceed to calculate the wall shear stress directly using the equation on the right hand side of equation 9 there. So no iteration is required with this approach, as we have the turbulent kinetic energy, directly compute y star, and then directly compute the wall shear stress. So in addition to this approach being able to handle flows with stagnation and separation, it's also a lot less computationally expensive because we don't need iteration. So just to give you an overview of how this process will work in the CFD code to help really put everything together, at the start of an iteration, what will happen is the CFD code will compute the dimensionless wall distance yPlus or y star using either of those approaches in equation 10. Of course, the approach using yPlus requires iteration, whereas the approach using y star does not require iteration. Then once we have yPlus or y star, we can then go on to compute the near wall kinematic viscosity, and we do that using equation 11. And when we compute the near wall kinematic viscosity, we use a different treatment depending on if we're in the viscous sublayer or we're in the logarithmic region. And if you want to see a full derivation for how we arrive at that value of the near wall kinematic viscosity, I'd advise you just having a look and checking out my previous video for a reminder on how we get that. But that treatment allows us to easily switch between a viscous sublayer and log law approach depending on the value of yPlus or y star. And then once we have the value of the near wall kinematic viscosity, we then finish off by computing the wall shear stress using equation 12. And as I mentioned in my previous video, once you've checked that out, the velocity gradient there in equation 12 is just given by the velocity at the cell centroid divided by the wall normal distance, which is of course a linear gradient, which is not correct, but then the product of that with the near wall shear stress, near wall kinematic viscosity will compute the correct wall shear stress regardless of the wall treatment that we used. So hopefully when you've seen the combination of my previous video and this video, the wall treatment of CFD codes should be a lot clearer to you now. So now, what treatment do real CFD codes actually use? Well, taking a look through the ANSYS FLUENT and the ANSYS CFX user guides, we find that these CFD codes use y star exclusively to compute the dimensionless wall distance and then the wall shear stress. OpenFOAM, on the other hand, gives the option of using yPlus or y star to compute the near wall kinematic viscosity. And these approaches are given by the nu-tu wall function and the nu-tk wall function, where nu-tu will be using yPlus, whereas nu-tk will be using y star. And so for OpenFOAM, both approaches are available. However, it's generally advisable in modern times to use the nu-tk version of the implementation to use y star rather than yPlus, because we avoid the need for iteration. At this point, before finishing, it's worth noting that regardless of the approach that the CFD code uses to compute the wall shear stress while it's processing, both yPlus and y star can be viewed as a post-processing operation, regardless of the choice of treatment that the CFD code adopts. And what the CFD code will do for this is take the final converged value of the wall shear stress and the turbulent kinetic energy and use those to compute yPlus and y star, which you can see there in equation 13. And I'd advise for yourself, if you have some time during your post-processing, just have a quick look at the values of yPlus and y star and confirm for yourself that they are actually very similar. But it's the choice of the variable that goes on under the hood in the CFD code that actually affects the processing and the solution. So just to summarize before we wrap up, where we use yPlus, that's because the velocity scale is based on the square root of the wall shear stress, whereas when y star is used, That's because the velocity scale is based on the square root of the turbulent kinetic energy. Y star is preferred in modern codes as it does not require iteration, and it's better for flows with stagnation and separation, where that wall shear stress may locally reduce to zero if we have reversed flow at the wall. And both yPlus and Y star can be viewed during post-processing for you guys to compare. And just a few useful references for you. I've got the ANSYS FLUENT user manual, and you want section 12.10.2 if you're looking through the manual and you'd like to see their guidance directly. And then in terms of papers, there's the original paper by Moser, Kim and Mansour, which shows how the experimental measurements for the wall velocity profile were derived, and you can also find a website that they host where you can actually get access to the raw data yourself as well if you'd like to have a look and plot those profiles for yourself. And then the final reference which I've got there is from Chalmers, University of Technology, and this paper does an excellent job of explaining a lot of these near wall treatments, and hopefully with the information I've given you in these slides today, that should make a lot more sense when you go through those slides. At this point, I'd like to thank you all for watching and supporting the channel once again. If you have any comments, suggestions, or noticed any errors, please leave them in the comment section below and I'll endeavour to get to those as quickly as I can. And another reminder for you all that you can check out my website if you'd like further information and summary slides for all of the presentations that I've put up here on YouTube. So if you really want to just dive in quickly and pull out key equations or go straight to a derivation and you don't really want to skip through the YouTube video, you can find that information also on my website. And thank you all for watching, and I look forward to hearing from you.